Hello, welcome everybody to our September webinar from Usomi. My name is Daniel Pinto. I'm the Vice President of Usomi, and apologies for my camera being switched off. I'm having some technical issues. Nonetheless, we're very happy to have a very special webinar today brought to you by our sponsor, BRACCO. As many of you know, there have been lots of AI approaches to COVID during the pandemic, and I think this will be a very nice presentation about one of those initiatives where the researchers try to use AI to better diagnose COVID. And without much further ado, I'll hand over to my co-moderator, Anna Andreychenko, which will introduce the first speaker. This is two speakers today, and we'll have a question and answer session at the end. So please feel free to add your questions to the Q&A or to the chat down below. And with this, Anna, please.
Yes, thank you, Daniel, for the introduction. Welcome everyone to our webinar. And now let me introduce our first speaker today. It's Giovanni Balbuzza. He is a digital innovation R&D project manager of BRACCO Imaging. Giovanni has over 15 years of experience in the biomedical imaging field, and in his career, Giovanni used data-driven approaches in various biomedical-related fields, including pharmacokinetics, drug design, optics, and so on. In 2018, he started working on AI for radiology at Centro Diagnostico Italiano as a scientific advisor, and in 2020, he was appointed as a digital innovation project manager at BRACCO. So, dear attendees, in case of questions, please type them in the Q&A box, as Daniel has said, and Giovanni, please, floor is yours.
Thank you, Anna. Can you hear me?
Yes, we hear you well.
Okay, so thank you, and I hope you can hear me well, and thank you again for the invitation and for the opportunity to show in behalf of all the AIforCOVID team the results of our project. It's really an honor for me. Trust me, it was a great project for me and a great collaboration. So again, my name is Giovanni Balbuzza. I'm the Digital Innovation Manager for BRACCO Imaging at the R&D department. And of course, I have been part of the collaboration for the AIforCOVID project. So what was the purpose of the project? The purpose was to use AI, but not for making diagnosis. The idea was to predict the risk of severe outcome for COVID-19 positive patients. So the idea was to use data about patients that were collected at the admission in the hospital to predict if the patient would have a severe progression of the disease, if he would require intensive care and so on, and let's say identify instead those patients that would have had a milder, less severe development of the disease. So what kind of value we think there's in such a tool? We think there are at least two values. One is the clinical one. So doctors may pay more attention on those patients that are at risk, at higher risk. And on the other hand, there's a management advantage, because when you know in advance that you will need a number of resources for managing a number of severe patients, then you can plan the use of resources in advance. So we are speaking about risk. Let's see how we define the risk. So let's start from the fact that we had available the data for each patient that has entered in our data set, including all the path of their disease. So we knew how it ended, let's say. So in the mild class, we included those patients that did not require ventilatory support. And also those patients that, for example, were sent back home and they never came back to the hospital for additional care. In the severe class, instead, we listed all those patients that required the ventilatory support up to patients that eventually died because of COVID. So in the data we use for training AI, we had both data about the patient at the beginning when they entered in the hospital, and data about how the disease progressed. This is needed by AI for training the predictive model we'll speak about later. So, and that's how, in general, then Professor Soda will give you more details about that. This is how we trained and we generate this predictive model. So we decided to collect both X-ray images of the chest and the clinical data. So clinical data, we meant all the data that were collected when patients were admitted in the hospital. So blood sampling data, oxygenation data, and so on. These data were fed into the machine learning and artificial intelligence machinery, and we asked this machinery to give us back a predictive model. So when we use these methods, we are used to say that machines are learning from data. And at the end of learning, what we have from this process is the model that only requires the input data, so the data you see on the left, and delivers prediction about a never seen before patient. This is the target actually of this process. But why we decided to put together images and clinical data? At the beginning of this project, we spoke with our colleagues, radiologists, and they report us they found a mismatch between the severity they found in chest X-rays and the actual outcome of the patient. So they found, for example, a patient with a severe disease looking at the images. And those patients maybe, they found some cases in which those patients went through a milder development of disease. And in other cases, it was the opposite. So they found a mild disease in the chest X-ray, but at the end, those patients had a severe outcome. So this mismatch was already known by our colleague radiologists, and then was reported also in some scientific works. So what we decided to do was we expected that the clinical data could complement the information that we had from images, and we expected and we hoped that actually the machine learning machinery could extract those data from that information from the additional clinical data we add to the data set. So how was the study planned and organized? So the study basically consisted of 3 steps. So the first was networking. Of course, we needed a network of hospitals for collecting the sufficient amount of data for AI. Everybody knows that AI requires a lot of data. So we started for building a network of satellite centers that joined the project. And it was not only about the data needs. So we also needed their opinion, their ideas, and we also needed support from the AI standpoint. And that's why we joined the Campus Biomedico, which is the university the Professor Soda, who is speaking next to me, belongs to, because we needed support for the technological standpoint. And given these multidisciplinary teams, we were able to define a study protocol which was, let's say, both clinically and technically making sense on both sides of the problem. The next step was, of course, having approval. So we got approval from our IRB. Actually, at the end, AIforCOVID was a data collection study. So it was not an interventional study. So it was quite, low impact. We decided not to change in any way the procedures that were used at the time where we collected data. So we collected data during the pandemic, during the first wave of the pandemic in Italy. So it was not possible actually to force doctors to adhere to a study protocol. So we decided to collect all data that were naturally generated following the procedure that were in place in every hospital that joined the project. Of course, the project was not impacting the patient in terms of risk, but we still had privacy concern. So we decided to use data that were anonymized when they left the hospital. So all the data that were moved towards Centro Diagnostico Italiano for data cleaning and the following data analysis were anonymized at the beginning. So how was data collection carried out? So we started with a study protocol. We defined with our colleagues what were the variable, the clinical data and the imaging data that would have been collected. And we decided to collect imaging data using DICOM files, quite obviously. And on the other hand, clinical data was collected using a homogeneous Excel template. And we decided what clinical variable to collect, and also we decided what unit measure to use, and we also negotiate about the meaning of some clinical data. You will see later will become more clear what does it mean, negotiated meaning of clinical data. So after collection, of course, we needed to do a lot of data cleaning, ruling out outliers and typos and so on. And then data was analyzed both at Centro Diagnostico Italiano and by BRACCO, but also by our partner institutions, including the Campus Biomedico in Roma, that is the university Professor Soda belongs to. And here it's a picture of the network. So we had 7 satellite centers. We collected data there. Actually, they collected data. It was quite a job for them, and they sent data through the promoter center that was Centro Diagnostico Italiano. And then data was cleaned and sent to these 3 institutions for data analysis and AI. And of course, we can only say thank you to all the hospitals and institutions that decided to join the project. And of course, it was not easy for them because of the pandemic. So again, thank you for joining the project. And last but not least, we collaborated with Amazon Web Services. So it was really important for the project having the support of Amazon Web Services. So we did 2 things with their technology. The first thing was to create a web-based way for collecting data. So we should not forget that when we started, we were forced to stay at home. So moving physical hardware was quite complex and it was not safe. So going to the hospital or just getting stuff from hospital was not really something we would like to do. So we had the help of Amazon to put in place a way of moving data safely, both from the IT perspective, but also from the health perspective, actually. Later, when the dataset was clean and was unified, and we had all this data, we used the AWS technology for building the website of the project and to let users to download our data, as we will see later. So now I described the methods and what we did actually, but let's give a look to what we got back, the results of the project. So first of all, we collected data and we made those data open access for research for everyone that through the website make requests of data for, of course, research purposes. So it's a still growing data set. We have about 1,000 cases today. We used less cases the time in which we wrote the paper. And we already had more than 80 downloads from all around the world. We built predictive models, and the description of the methods and the results are now described in a paper that was recently accepted by Medical Image Analysis, and Professor Soda will speak about that in details next to my presentation. And again, data is available for download, but it is also browsable, and you can explore our data set through the website in a quite easy manner. And very recently, through the website, we added another functionalities. We made available one of our AI tool for prediction that can be used with your own data. You just need to request the credential for use this tool and enter your data, and you will see how AI can provide you back a prediction of how the outcome, the development of the disease would have been for that patient. So again, the dataset it's quite a mixed dataset. We have both clinical data and X-ray data. Data were collected during the first wave of emergency in Italy, and we have more than 1,000 cases now to be used for research. One important point is the dataset is still growing, and of course it is open to contributors. So anyone who wants to add his data to our dataset, just email us. You will find you can find the email of the project on the project website, and we will very happy to add your data to the dataset and make available those data for everyone. Clinical data, we collected a list, very long list of clinical parameters. And I don't want to go through all this data. Of course, we had for some parameters some missing data. This was because procedures were not homogeneous among the hospitals. So that's why we have mixed availability. And we also collected therapy data. So therapy about the data about the therapy that was delivered to the patients. Of course, this data was not used for building the predictive models because the therapy was not available at the time of admission. So because the therapy depended on the outcome somehow. So we didn't use this information, but it's there. So you can use also this information when you download the dataset, you will find it there. So, and what about the images? Again, it was an emergency situation. We cannot force doctors to select the way images were collected. We could only ask them, please send us all the images you have. And they sent us actually mixed types of images, both from the device perspective. So we had analog images from digital devices, but also images acquired with the patient standing and the patient at bed, the patient in a sort of ambiguous position, and sometimes the patient cannot be compliant to the requirement for a perfect acquisition. So that's why in this list of images, we had examples of images with a good contrast, images with a lower contrast, images, bad images, low quality if you want, images where patients were, the patient was probably not totally compliant with the acquisition protocol, very low quality, let's say sort of mixed type of artifact, also foreign objects. So we could not ask to, we didn't ask actually doctor to remove or make a selection on those images. We just collected everything. And we think this is sort of plus of our data set, because if we want machine learning and AI to be useful in this condition, they have to be able to deal with this kind of variability. Okay, and this is a picture of where our data set was downloaded. We had requests again from all over the world, and we are really happy and proud that it has been already downloaded in such a number of countries all around the globe. And the data set of AIforCOVID was also used for an hackathon. An hackathon is a sort of contest for data scientists, so they compete for making the best predictive model. This one was organized by the Helmholtz Institute, and it was held during April 2021. They had 70 participants, and both Centro Diagnostico Italiano and BRACCO Imaging were very happy to sponsor this initiative. Finally, this is what Professor Paolo Soda will speak about in details, but I just wanted to have this front page of our paper. We are really proud that our work was accepted by Medical Image Analysis, which is a very, very important journal in this field. And again, thank you to everyone who joined this effort of analyzing data, collecting data, putting together the paper, and special thanks for all the work to Professor Paolo Soda that actually drove the writing of this paper. Okay, now I would like to spend some seconds to show you how our AI tool has been very recently made available through the AIforCOVID website. This is the home page of the project. And you see there are some buttons, and one of these buttons, this one, Run AI Prediction, will let you assess the AI-based tools that we made available. So you just need to click on that button, and this will lead you to this login page. You need to enter your credential. So we ask for a second request. If you already requested credential for data download, this is an additional request because this AI tool is sort of sensitive tool. This is not a medical device because it is not approved. It's a tool for research, and we really want to avoid that it is misused by, let's say, the general population. So that's why we ask users to give some more information about who they are, in which institution they work, and so on, because we would like to avoid again the misuse of this tool. Then the user lands in this page in which he is asked to enter clinical data that are then used by the model for predicting outcome for the patient. So again, there's a list of clinical data, and the user needs to enter parameters, values, sorry, and then the user is asked for an image, so a DICOM file actually that containing the chest X-ray for that patient. And then data is loaded into the system. So data is especially, let's say, DICOM metadata is anonymized on the client side, so by the browser itself, and then anonymized data are sent to our AI engine, which is again based on AWS technology, and through when the user push this run AI prediction button, and what you get back is a report containing the results of our AI tool. So let's give a look, sorry. So let's give a look to the content of this report. So there's a first section containing a summary, some details about how the model has been developed, and also a summary of the data that has been entered by the user. And the second part of the report is contains the risk score. So it's the risk for the patient to have a severe outcome. And it goes, of course, from 0 to 100%. And we also added a plot in which the patient clinical features, clinical variables, and the risk score are plotted together with the average for the mild and severe class. Just to say, it's sort of a supportive tool to let the user understand why the model decided to output that risk score for the patient. And this is the end of my presentation. I just want to remind you to show you the right web address of the project website. So it is here. And again, I would like to thank all the people and institution, hospital that joined the project and collaborate for achieving these, for me, amazing results. And I would like to thank you for your attention, and I'm ready, of course, for answering any question. Thank you.
Yes, so thank you, Giovanni. That was a very nice and clear presentation, I think, and it's really been a great effort that you put into this project. So I'd like to just give the mic to, again, to Paulo Soda. So he graduated and has a PhD in biomedical engineering and is working mostly in computer science, of course, with the university campus of biomedicine in Roma. And since 2005, he has been deeply involved in AI and machine learning research and, of course, image analysis as well. And yeah, with that, I hand the floor to you, and I'm happy to, or interested to see the technical side of the project.
Good afternoon to everybody, and thanks, Daniel, for the introduction. So in the second part of this webinar, we will discuss the technical parts of this work. Here is a picture of how the pipeline is organized from data collection, already described by Giovanni, towards data imputation, image standardization, lung segmentation, feature extraction, feature selection, and the learning process. We will not discuss all these steps, but I'm putting the attention on the most important steps, or the steps that need more technical details to be presented. In our work, we discussed 3 AI-based approaches, named as an crafted approach, hybrid approach, and end-to-end deep learning approach. And now we will review them. Let's start with the first one, the uncrafted approach. As the name said, this approach is based on this approach makes use of uncrafted features. And these features depends on first order and second order descriptors that are computed from the segmented lines. That means from segmented lines, we use traditional texture analysis based on relative descriptors and set of map analysis, and we put together these data with the clinical information that Giovanni described before. And then we run a feature selection stage that fed a machine learning, several machine learning classifiers, support vector machine, a random forest, and a logistic regression that predicts the final outcome. But as we know, numbers are king, but the quality is queen. That means we strongly need the feature selection stage. And this feature selection stage is organized into phases. In the first one, we run a course phase where we pre-select image features being uncrafted or deep features like I will introduce after, and where we apply a univariate analysis based on motor information. And in a second step, we run integration analysis where we merge the pre-selected imaging features with the clinical data. And we run a wrapper approach, which is a recursive feature elimination cross-validation selection. This is an approach that runs a pruning, is a pruning method that starts considering all the possible features in the dataset and recursively eliminates the less important according to a score. We run a 5-fold cross-validation training set that permits to avoid any bias in the feature estimation. And we use the same learners in order to maximize the information power of the features. And then we can move to the learning stage, because in the hybrid approach, the point is that the features are not uncrafted, so are not based on any mathematical formulation and mathematical formula, but they are extracted from using convolutional neural networks. These convolutional neural networks have been pre-trained on the ImageNet dataset, and after freezing some layer, they have been applied, fine-tuned to our repository. That means that we run some epochs to fine-tune the network on our dataset, even exploring the possibility to pre-train on similar array chest X-ray dataset. And then we extract the representation provided by the convolutional layers. As reported in the slide, we extract the information available before the fully connected layers. And this feature vector is after the flattening of the convolutional representation is integrated again with the clinical data. And again, we run the two-step feature selection that put together first pre-select the image features and then merge them with the clinical data. After that, we still use some shallow classifiers like the support vector machine, random forest, and logistic regression for the sake of comparison with previous approaches. But our work would like to provide a baseline for other researchers and practitioners that would like to explore this dataset and use to fight the pandemic. And that's why we explore a third possibility that is given by the use of an end-to-end deep learning approach. So our methodology spans from the uncrafted approach up to the fully deep learning approach. In the fully deep learning approach, we need to put together the clinical data and the imaging features. So that's why our network is a bimodal network. That means on the left side of the slide, you can see the architecture of the deep network processing the clinical data. While on the right side, you can find the organization of the deep networks processing the images. It is based on the well-known ResNet 50 architecture, plus a couple of dropout and dense layer that permits to better process the data. And then we have the concatenation layer, the one reported in the middle in orange, that permit to put together the features coming from the clinical data and the images. Let's remember that these features are automatically learned by the deep network. What about model validation? Model validation is a very important point in any AI assessment. So first of all, we would like to note that we do not perform fine-tuning of the hyperparameters of the classifiers, because we are not interested in the best absolute performance, but rather we would like to provide a baseline. And this is also because it is empirically known that the use of tuned parameters cannot significantly outperform the default values of a classifier. And what about the evaluation experimental approach? We performed two types of validation. The first is based on the k-fold cross-validation, where we tested a k equal to 3 and k equal to 10, repeated 20 times. And in the published paper, we reported the values achieved by 10-fold cross-validation, even there are not any significant difference with 3-fold. In a k-fold cross-validation, of course, we guarantee that training, test, and validation set are separated, but we do not guarantee that images belonging to different centers are assigned to different sets. That means that images that belongs maybe from the hospital in Milan, San Matteo, can be assigned to the training set and to the test set. That's why we also run a lay one center route cross-validation. It is shortly referred to as local cross-validation in the following slide. That means that the images belonging to one of the hospital is assigned to the test set, and the other images belonging to the other hospital are assigned to the training set. And then we iterate this approach, changing the center assigned to this test set. This permits to assess what happens when without mixing images from the same hospital. What about the metrics? So in the paper, you can find results reported in terms of accuracy, sensitivity, and specificity. In the following, I'm showing you results in terms of accuracy because sensitivity and specificity are almost balanced, and in order to not avoid a lot of numbers, I'm focusing on the accuracy. We also run statistical analysis, running pairwise comparison when needed, or multiple comparison based on a Crucius-Wallis test followed by Durance test with buffer correction. But let's move to the results. First, I would like to focus on the clinical data. So using only the clinical data and a shallow classifier, we are able to get 75% of accuracy, and the feature selection stage identified 11 clinical features that are most informative. When we use deep networks, these results drop to 78%. And this is essentially due to the fact that the deep network must be trained from scratch. That means that we cannot enjoy any fine-tuning, any previous knowledge from different domains to pre-train the weights of the network. So this maybe can affect the result, and we expect that with a larger data set, this effect can be mitigated. But what happens when we run local cross-validation? That means the cross-validation based on the sample. We observed a drop in performance, both when we use shallow machine learning methods and when we use deep networks. This is essentially due, in our opinion, to the fact that there is some variation of the data among the centers that limit the generalization capability of the learners. One more slide about the clinical data. This picture reports the relevance normalized to one of the clinical features. And each color of the bar represents the different learners use. If we can observe that LDH is the clinical information that for all the learners is very representative. And when we use these two signs, the plus and the asterisk, to represent that the features is included in the best results we are showing today, both in k-fold and local cross-validation. That means that several features are very stable and they provide informative information. As you can see, we have the age, the rate, oxygen saturation, dyspnea, the diabetes, and so on. Let's now focus on the results achieving using only chest X-ray images. I'm reporting here, I'm showing you the performance achieved when we're using the uncrafted approach on the left, the hybrid approach in the middle, and the deep learning approach on the right. What we observe in general is that the use of images does not achieve the same performance obtained using the clinical data, whatever the method. And we still observe a drops in performance in terms when we move from key-fold cross-validation to Lee-one central route cross-validation. That means that the variability in the image quality among the centers can significantly impact the result. We also observe that deep learning has the possibility to get the largest results in terms of accuracy. This is mostly due to the fact that the convolutional layers the CNN uses can learn effectively interesting representation from the images. But again, as one more focus about the information that can be retrieved from the images. As you remember, I said that we run feature selection, selecting the most informative imaging features. What we did in this picture is that we take the most informative features retrieved by convolutional neural networks, and using the BRACCO, that is a method for explainable AI, we are able to project this information back on the images. And we would like to understand if the reduction, the compression information performed by feature selection can affect the result and the identification of the most significant error in the images. What you can find here is the comparison of this issue. So here is the activation map provided by the CNN when we are using all the neurons in the flattened layer. That means all the information retrieved by the convolutional layers in the network. And here is the activation map retrieved using only the 40 most selected neurons. As you can see, the activation maps are quite similar, even if there are some differences in the color. That this is mostly due to the reshape to the rescale of the intensity map. And again, we can observe a similar behavior here for a patient belonging to the severe class. This suggests us that the CNN has the ability to learn representative information from the images. Even if we reduce the number of neurons, we reduce the number of neurons to the most informative one. Okay, let's move to the result we achieve putting together images and clinical data. As you can see here, best results are achieved by the hybrid approach with almost 70% of accuracy. And even the others two approaches get closer performance. This suggests that the integration of the two modalities in some cases improves the classification performance. It's not a very large improvement, but what is interesting to note is that the improvement is quite more important when we run Lee-one central route cross-validation. That means that in the multimodality, can provide most powerful model learners when we are applying them in a more stringent, more strict scenario where the variability is larger. For some further consideration before moving to the comparison, to another deep comparison, is that the approach to the computer and crafted features unfavorably compares with the use of convolutional neural network. And between the hybrid approach and the deep network approach, we didn't find any significant approach from a statistical point of view. While we observe significant difference in terms of statistical test when we compare the uncrafted approach with the hybrid approach and the deep learning approach during Lee-one central route cross-validation. In this slide, I'm showing you the a priori probability in our dataset of the anterior-posterior images with respect to the posterior-anterior projections for the different for the 6 hospitals involved in the study. As you can see, the prior of the anterior-posterior is much larger than the other one. So we measure the performance that we achieve on only on anterior posterior images and only on posterior anterior projections. And what we find is that the accuracy on the AP images is larger. This can sound strange because we can say, okay, but AP images are mainly used for the acquisition of bedridden patients, so we expect a lower quality. But this is interesting results of the study. That means that the model is able to extract knowledge even from images with low quality, opening the possibility to be used even with bedridden patients and being a useful tool in an emergency department. This can be also from a technical side due to the large prior available in our dataset, of course. But the question that we can have is the one reported here. Are images really useful? And this slide summarizes the results in terms of accuracy, comparing the results achieved by the clinical data only, the images only, and the multimodal approach, while we're using key-fold cross-validation and Lee-Wansson-Trout cross-validation. As I told you before, the use of multimodality improved the data, improved the results, even not so much. But of course, ours was an explanatory investigation where we used some baseline approach, providing also baselines for other people. What I would like to show you is that new results that are still unpublished, submitted from our group, show that images can be successfully employed. And that means integrating clinical data with images, we are able to get an accuracy up to 80% with a very small standard deviation. These results are statistically different from the previous one. These results have been achieved developing new types of an ensemble of deep networks that work together in a fully joint learning approach with clinical data. They are still unpublished, but that means that this repository has the possibility to foster research in a prediction or with predictive power to fight COVID pneumonia. Let me conclude this presentation. One of the main limitations of the study is the lack of full standardization of images, clinical data in the dataset, as Giovanni already said. But even if this is a limitation, we deem this is a challenge for AI researchers because the dataset reflect real-life situation where the data are not so clean. This is not an in vitro experiment. We can say something in vivo that reflect what happens really in the hospital. It's also interesting to note that we find out that some clinical data are really informative, like age, LDH, oxygen saturation, dyspnea, sex, and so on, confirming the results reported in other studies by other researchers. Of course, the poor standardization of images has led to a very hard classification problem. We have a lot of variability due to the not standardized image acquisition condition and the various medical devices involved. Our repository is still maybe the largest one public available today, and it displays side by side with a similar effort to using CT images, but that of course needs different equipment and different procedure to collect the images. And I would like to remember that it is a long-term initiative that is still collecting other images that can be added to the repository and they can foster further research and better results. So thanks for your attention, for your interest in our work.
Yeah, thank you very, very much, Paolo. That was a very nice presentation. And I think you are absolutely right that we see a lot of AI stuff coming out, but this is mostly not on real clinical data. So I think that's really a huge bonus in your study. So just a couple of questions, just out of interest. Did you look at how much the quality of like the image or the segmentation of lungs or whatever did impact the results? So could you say, well, there's, for example, if the image is particularly bad, the algorithm won't work as well, or did you look at that?
Okay, thanks. I skipped the details about the segmentation. For the segmentation, we use the UNet architecture pre-trained on another under 2 chest X-ray repositories. And we investigated what happens if we are using automatic segmentation or manual segmentation performed by expert radiologists. What is interesting is that the performance using of our AI algorithms running on automatic segmented lungs are even a little bit better than performance achieved using manually segmented readers, although we do not observe any statistical difference from that. That means that the quality of automatic segmentation on chest X-ray has reached today a very good performance, even using low quality images like someone that we have in our repository. And what we observe is that some slight variation in the borders of the lung do not affect the results.
All right. So Anna, do you want to go next or?
Yes, sure, Daniel. Yeah, Paulo, thank you very much for your presentation. I think it was really interesting, and all the different approaches that you have compared. And as we see now that also a common trend now is to include clinical information to enrich image data and to make diagnosis more correct, more precise. And I also have a question for you. So what do you think is the major technical contribution of your paper and your analysis?
I think that one of the major contributions of the paper, of course, further to the data availability of the data set, is the idea that we provide a wide benchmark of several approaches spanning from uncrafted to fully deep learning. And although not reported in this presentation, we really ran a lot of tests exploring maybe more than 15 different convolution architectures and different learners and so on. So and all this information are reported in the paper and in the supplementary material that came with the paper. And I deem that this can provide a baseline that the other researchers can use to compare their results and can also, this is also a baseline to provide a fair comparison among the results, because the fairness of AI is an hot topic today. And what we would like to avoid is the wrong use of this data. So the baseline is used to provide a fair comparison among the researchers so that an improvement can be clearly motivated, it can be clearly explained to the readers.
Okay, thank you. And what would be your advice to other researchers from which approach to start with? Because what you have shown that truly deep learning is the most favorable one, and you show that you really achieved even high accuracy now. But could you give some, I don't know, some like tips where to start? So what to choose, handcrafted, hybrid, or end-to-end deep learning for any problem? Yeah.
Yes. From our experience, I suggest starting with hybrid or deep learning approach. And my suggestion is to start exploring joint or multimodal learning. So the possibility to train end-to-end different networks, exploiting the back propagation of the weight and the loss on both the clinical network and image network. And a recent trend in COVID image analysis is the possibility to use an ensemble of deep networks that work together. And what the results are still unpublished, submitted, that I shown you before, or in terms of 80% of accuracy, has been achieved using an ensemble of deep networks, but this ensemble is optimized according to a loss function that try to maximize not only the accuracy, not only the precision of the recall, but also the diversity among the networks that are put together in the ensemble itself. So my suggestion is to explore multimodal learning, because it is the new research trend in deep learning in general.
Great. I was wondering, I mean, obviously there's a lot of effort needed to collect the data. Maybe this is a question to Dr. Valbusa, I don't know. So how did you actually collect the data? Was that a lot of manual work, or could you automate that to some extent?
Yeah, it's still there's still a lot of manual work, especially on the satellite center side. So we had actually interns collecting data and transferring data from the paper to the digital format. It's something that, well, let's say, we didn't find alternatives to that. So data is still not totally ready to be used in a sort of automatic fashion in the hospitals. So the technology is not totally there for the full, let's say, exploitation of data. On the other hand, data science, when data are in digital formats, can lead to very fast cleaning procedure, and it's really easy today to develop also specific tools that are tailored for making even faster the cleaning process on data.
So, I mean, or maybe a question to both of you, what's the main takeaways? What did you learn in terms of technical or even clinical information that you think is useful for further projects?
Well, in general, I think we understand and we show another time that with AI you can, and let's say starting with a relevant, a big data collection, you can extract from data a lot of value, and also that the technology is there to let every users to have access to the AI technology. So through the AI tool that we recently made available through the website. So let's say the take-home message is that AI is there and can be used. There's still some, it's still hard collecting data, and let's say it's somehow complex to understand how to move forward toward big and complete and let's say very useful way of using those data, which are there, but it's not totally clear how to use them and to convert them into something that can be used with the current technologies.
I do agree, absolutely. So Anna, is there any more questions from your side or from the audience? I didn't see much. Let me check again. No, maybe Anna, one last question. I think we're very good on time.
Yes, indeed, we're very good on time. Yes, and how do you see to develop further this project? So are you going to focus on different use cases or include chest CT scans as well? What are your plans?
Well, so the project is not closed. I mean, we are still collecting data, so it's still this is still ongoing. But of course, we are looking to other applications, and at Centro Diagnostico Italiano in particular, our colleagues are starting a project about the post-COVID disease. So all the sequelae that some patients that are already out of COVID have in terms of impact on other organs and so on. So it is something that sort of started with AIforCOVID, and they are developing towards the post-COVID problems.
Okay, yeah, that's a very important problem as well.
Yeah.
Yes,
Yeah,
so yes,
yeah,
Daniel,
Anna, please go ahead. No, please.
Okay. No, so I would like to thank our speakers tonight. I think it was very interesting and very nice initiative, and I hope it's going to go international as well. And you will get more attention, more data to bring it to society. And help everyone with this open science which we are doing now. And I would like to thank our attendees as well, and my co-moderator Daniel and Paola, who has organized this webinar. Yeah, thank you. And Daniel, please.
Yeah, no, nothing to add from my side. I think it was really interesting, and obviously that was a lot of effort. I really appreciate that. I think it's a great effort you put into that, and yeah, thanks to everybody. Thanks to you. Thanks to the speakers. Thanks to Anna. Thanks to all the members in the audience, and of course, thanks BRACCO for sponsoring. And yeah, I hope we'll see you soon again. And thank you, everybody, and have a nice evening. Bye bye.
Bye bye.
Bye bye.
Bye bye.